Okay. Again, of course, let's look at some pictures, which, okay, easier to understand. What are we looking at here? Solar panels. What is this? So-called solar cell, because every one of these panels actually made up of many individual solar cells, right? What I'm looking at is a so-called polycrystalline or multicrystalline silicon solar cell. Okay. The process of diffusion is very, very important for silicon solar cell. For example, you learned in physics p-n junction, and in order to form the so-called emitter, the n layer over p layer, to form the p-n junction, we need to control the silicon diffusion. Actually, the phosphors quite often diffusion into silicon. Okay, and the similar emitter diffusion is very important for what I'm pointing at. Transistor, actually, is called a wafer, a chip. A chip, a wafer, people fabricate it into many small chips and package and put them into cell phone computers. And the similar p-n junction emitter formation is very, very critical to these things, the diffusion formation. Okay, what I'm looking at here, battery. In particular, probably this flat one is lithium-ion battery. What is this guy? Automobile, but right now you probably heard of it or probably even seen the so-called EV, electrical vehicle, based quite often on packaged lithium-ion battery, and the lithium ion releasing from an insertion into the electrode. That involves diffusion. Going through the electrolyte also involves diffusion. Make sense? Very, very important application. And of course, there are some other things like oxygen vacancy diffusion for oxygen sensor for your automobile. Oxygen sensor. How do you know you have a clean burn of your fuel? You need an oxygen sensor. Okay. And oxygen vacancy diffusion. We'll talk about it. Hydrogen transport. How do people separate hydrogen gas from CO2 gas? Let's say for many chemical process. For one possible way is using a so-called palladium membrane, a very thin metal membrane, and the hydrogen gas, hydrogen atom among all the atoms is the biggest or smallest? Smallest. And the hydrogen atom can go through many metals like palladium to separate hydrogen gas from the much larger, let's say, nitrogen gas or carbon dioxide gas. Make sense? So that's also involved diffusion. Or let's say when you wear a glove, you want to protect yourself from dealing with chemical, the gloves slows down the diffusion of hazardous chemical into your skin. Make sense? Diffusion is everywhere. We have to understand it. And there are interfaces. What I'm looking at would be a what's your guess of this guy? This is a hand. What is this guy? Actually, this is a big piece of casted solidified silicon, high purity silicon. For what application? For this guy. For so-called polycrystalline silicon solar cell, people cast liquid silicon into a mold, solidify, and cut them into thin slices, make them into silicon solar cell. And for these, the green boundaries, do you see on this plot, on this figure, there are different shades? Do you see this here? And between one uniform shade and the neighboring shade, that is a green boundary. And actually, if you have to guess, the more the boundary, the better the solar cell, or the less the boundary, the better the solar cell. For silicon solar cell. Yeah, lesser boundary, because quite often the green boundary is a so-called the defect side. The electron and hole would tend to recombine, annihilate over there. So you want to avoid it. You want to avoid green boundary. Make it less. How do you control your production process to make it less grain boundaries? Make sense? On the other hand, for some other solar cell, like CIGS solar cell, the grain boundary doesn't seem to be mattering that much on silicon. Okay, so the interface is important. Solidification, as I said, this guy is obtained from liquid. You're pouring liquid, you are solidifying, and in the process, you are controlling going from liquid to solid. You want to control the amount of grain boundaries, solidification process. For this, what am I pointing at here? Apple Watch, right? And for Apple Watch, and people said, okay, the front piece of transparent glass is actually not glass, they call it sapphire, which is, for chemists, sapphire is single crystal aluminum oxide, Al2O3. Sapphire, single crystal, actually many of these are the image, single crystal. And how do you get single crystal aluminum oxide? You still have to go from liquid into a solid, solidification process. Here you want to completely single crystal, you want to completely eliminate grain boundaries, but can you eliminate surface? No, right? It always has surface. You can eliminate grain boundary, but not surface. So how do you control the process? How do you understand the process? Polycrystalline was a single crystal. Okay. And diffusional transformation, what I'm pointing at here. L-plane. L-plane used to have a lot of aluminum alloy and titanium alloy. And all those aluminum alloy, especially for aluminum alloy, what's the difference between your L-plane aluminum alloy versus your food wrap aluminum? Which one is stronger? Your food wrap aluminum versus L-plane aluminum. Which one is stronger? Common sense, L-plane, definitely. Your food wrap aluminum, you don't want to use too much force to bend it, right? That aluminum for food wrap foil is very soft, very, very soft. But by doing a so-called phase transformation control, we can make the aluminum, pretty much all aluminum, with some impurity, make them much higher, much stronger, much harder for airplane applications related to phase transformation, diffusional transformation. There's also diffusion-less phase transformation. We'll talk about it, touch upon it. For tool steel, for machinery, as I said, that knife or saw blade or sword blade or saw for cutting, those materials need to be very, very hard. And quite often they involve diffusion-less transformation. And how do we understand them? For auto, also for construction. In the automobile framework, the steel, people are using high-strength steel, ultra-high-strength steel. Why? If the strength of steel can go higher and higher, which means I can use less and less of the steel for the automobile body, and what benefit do I get? Less and less weight, which means consume less and less energy. And also, if it's strong, it also the passengers are safer. Make sense? So there's a lot of information, a lot of applications. Toughened ceramics for abrasives. Okay, we said, okay, how do you cut these things? How do you polish these things? These are very, very hard material. How do you cut polish? You need to use even harder material, quite often some type of ceramics. Of course, including diamond, but here we are less concerned with diamond. There will be toughened ceramics for abrasives, many of them. Okay, involve diffusion-less transformation. So in essence, what we are talking about, the kinetics and phase transformation are important. They are important to almost all. I would say almost all, because for certain application you don't care, because you don't need it to last long or whatever. But for many critical applications, it becoming more and more demanding. And the kinetics and phase transformation are important to understand those processes for the material. and they have application in many different fields. Okay.